let's take an alternative view of the EM algorithm. And the material here is based on a paper by Neal and Hinton in 1998. Consider the following objective function, where the numerator is the joint likelihood of x and z given theta. And the QZ here is any distribution on Z. It will be a PDF if Z is continuous, or a probability mass function if Z is discrete. So the right hand side, we have our data x, which is given, and Z will be integral over because we take expectation of Z outside with respect to Q. And theta is unknown, and the distribution Q is also unknown. So this is a function with two arguments. One is theta, another is this unknown distribution over Z. Let's play with this objective function using the same trick we used before. We're going to factorize the numerator, the joint, as a marginal of x and also conditional of z given x. Now, because the p of x given theta has nothing to do with z, so we can take this term outside the expectation. So we will have the function f equal to two terms. The first is the log of the marginal of x given theta and minus another term, which is actually the k-out divergence between two distributions over z. Now, to maximize f, let's try to maximize each term, try to make each term achieve its maximal value. Now, how to make the first term achieve its maximal value? We're just going to let our theta to be the MLE, and that maximize p of x given theta. And for the second term, the minus a k-out divergence. So we want to make the k-out divergence as small as possible, and the smallest value we could achieve is 0 by setting q of z is equal to p of z given x, and theta is equal to MLE. So in other words, we can obtain the MLE of theta as a byproduct of maximizing this f function. Now, how we maximize the f function, you're going to find out the EM algorithm is essentially a coordinate descent algorithm on f. Meaning at the tth iteration, given the current value of theta, let's find out the optimal Q. Well, as we discussed before, the optimal Q will be, we want to set the Q only appear here, so we want to set the k-out divergence to be 0. So the optimal Q will be just p of x z given x, and the theta being whatever value you have right now. So this is optimal Q. And then next, given the optimal Q, let's update theta. Now, given Q, when we try to update theta, we can ignore this term because it has nothing to do with theta. And then you're going to find out this function is basically the g function in the EM algorithm. So when we try to update theta given Q, that's basically the m step in the EM algorithm. This alternative view of EM basically tells us that there's no difference between the E step and M step, and they can both regard it as M steps because we are iteratively optimizing this function f. And this provides some justifications for some variants of EM algorithm, where we only do a partial updating or partial implementation of the E or M, as long as the corresponding Q or theta are better than the current value, meaning we are improving the f function at each iteration. And also in some of the applications, this is a NIPS paper you can check, where we have some constraints on the Q function. In this alternative view, because the E step is essentially an M step, so we can easily incorporate that constraint in the optimization. Another major advantage of this alternative view is that it naturally leads to the variational version of EM algorithm.